In the first stage of the Calvin cycle, a CO2 molecule is incorporated into one of two 3-carbon molecules, where it uses up 2 molecules of ATP and 2 molecules of NADP, which had been produced in the light-dependent stage. The 3 steps involved are: the enzyme Rubisco catalyzes the carboxylation of ribulose 1,5-bisphosphate, RuBP, a 5-carbon compound, by carbon dioxide in a 2-step reaction. The product of the first step is enediol enzyme complex that can capture CO2 or O2. Thus, enediol enzyme complex is the real carboxylase/oxygenase. The CO2 that is captured by enediol in second step produces an unstable 6-carbon compound called 2-carboxy-3-keto 1,5-biphosphorbutol that immediately splits into 2 molecules of 3-phosphoglycerate, a 3-carbon compound. The enzyme phosphoglycerate kinase catalyzes the phosphorylation of 3-PGA by ATP. 1,3-bisphosphoglycerate and ADP are the products. The enzyme glyceraldehyde 3-phosphate dehydrogenase catalyzes the reduction of 1,3-BPGA by NADP. Glyceraldehyde 3-phosphate is produced, and the NADP itself is oxidized and becomes NADP+. Again, 2 NADP are utilized per CO2 fixed. The next stage in the Calvin cycle is to regenerate RuBP. 5 GIP molecules produce 3 RuBP molecules, using up 3 molecules of ATP. Since each CO2 molecule produces 2 GIP molecules, 3 CO2 molecules produce 6 GIP molecules, of which 5 are used to regenerate RuBP, leaving a net gain of 1 GIP molecule per 3 CO2 molecules. The regeneration stage can be broken down into a series of steps. Triose phosphate isomerase converts all of the GEP reversibly into dihydroxyacetone phosphate, also a 3-carbon molecule. Aldolase and fructose 1,6-bisphosphatase convert a GEP and a DAP into fructose 6-phosphate. A phosphate ion is lost into solution. Then fixation of another CO2 generates 2 more GEP. F6P has 2 carbons removed by transketolase, giving erythrose 4-phosphate. The 2 carbons on transketolase are added to a GEP, giving the ketose xylulose 5-phosphate. E4P and a DAP are converted into pseudoheptulose 1,7-bisphosphate by aldolase enzyme. Pseudoheptulose 1,7-bisphosphatase cleaves pseudoheptulose 1,7-bisphosphate into pseudoheptulose 7-phosphate, releasing an inorganic phosphate ion into solution. Fixation of a third CO2 generates 2 more GEP. The ketose S7P has 2 carbons removed by transketolase, giving ribose 5-phosphate, and the 2 carbons remaining on transketolase are transferred to one of the GEP, giving another SHU5P. This leaves 1 GEP as a product of fixation of 3 CO2, with generation of 3 pentases that can be converted to Ru5P. Or 5P is converted into ribulose 5-phosphate by phosphopentose isomerase. SHU5P is converted into RUP by phosphopentose epimerase. Finally, phosphoribulokinase phosphorylates RUP into RuBP, ribulose 1,5-bisphosphate, completing the Calvin cycle. This requires the input of 1 ATP. Thus, of 6 GEP produced, 5 are used to make 3 RuBP molecules, with only 1 GEP available for subsequent conversion to hexose. This requires 9 ATP molecules and 6 NADP molecules per 3 CO2 molecules. The equation of the overall Calvin cycle is shown diagrammatically below. Rubisco also reacts competitively with O2 instead of CO2 in photorespiration. The rate of photorespiration is higher at high temperatures. Photorespiration turns RuBP into 3-PGA and 2-phosphoglycolate, a 2-carbon molecule that can be converted via glycolate and glyoxylate to glycine. Via the glycine cleavage system and tetrahydrofolate, 2 glycines are converted into serine plus CO2. Serine can be converted back to 3-phosphoglycerate. Thus, only 3 of 4 carbons from 2 phosphoglycolates can be converted back to 3-PGA. It can be seen that photorespiration has very negative consequences for the plant, because, rather than fixing CO2, this process leads to loss of CO2. C4 carbon fixation evolved to circumvent photorespiration, but can occur only in certain plants native to very warm or tropical climates, corn, for example. The immediate products of one turn of the Calvin cycle are 2 glyceraldehyde 3-phosphate molecules, 3 ADP, and 2 NAD+. Each GEP molecule is composed of 3 carbons. For the Calvin cycle to continue, RuBP must be regenerated. So, 5 out of 6 carbons from the 2 GEP molecules are used for this purpose. Therefore, there is only one net carbon produced to play with for each turn. To create one surplus GEP requires 3 carbons, and therefore 3 turns of the Calvin cycle. To make one glucose molecule would require 6 turns of the Calvin cycle. Surplus GEP can also be used to form other carbohydrates such as starch, sucrose, and cellulose, depending on what the plant needs.